Lesson 6. Capacitance. Section 6.1. Capacitance. This is a cross-sectional view of two concentric spherical conductors. One is the sphere with a radius of a1 meters, and the other is a shell with an inner radius of a2 meters surrounding the sphere. Suppose that charges of positive q coulombs are placed on the sphere. Then the charges will be distributed over the surface CS1. On the inner surface CS2 of the shell, charges of negative q coulombs will be attracted and cover CS2. Charges of positive q coulombs will be induced and distributed over the outer surface CS3. If the shell is grounded, what will happen? Electrons flow into the shell through the grounding line. The electrons neutralize the positive charges on the outer surface CS3. In this static state, the electric field intensity outside the shell conductor is zero. The electric field is said to be shielded. The electric field exists only in the gap between the two conductors. Then, by applying Gauss's law, the electric field intensity E at R is obtained as shown in this equation. The potential on the surface of the sphere with respect to the inner surface of the shell is derived as in this equation. This potential difference is called voltage. The unit is volt. The ratio of charge to voltage is defined as capacitance. Capacitance is denoted by C. The unit is farad. The capacitance of these concentric conductors is given by this equation. Next, let's find the capacitance of two conductor plates, placed parallel to each other. This configuration is called a capacitor. The length and width of the plate are L meters and W meters respectively. The facing area A is given by L times W square meters. The separation distance is D meters. An insulating plate or a dielectric plate is inserted between the plates. D also represents the thickness of the dielectric plate. This is a cross-sectional view of the plates and the dielectric plate. One plate is grounded. Positive charges are placed on the other plate. The positive charges induce electrons in the opposite plate. Then, the charges are distributed over each surface attracting opposite charges, and settle into a static state. These are electric flux lines generated by the positive charge. Most of the lines are straight and parallel, perpendicular to the surface of the plates. On the fringe, lines extend outward. This irregularity of flux lines at the fringe is called fringing effect. For a practical capacitor, the fringing effect is negligible. Because the distance d is much shorter than the length L and the width W. Let's take an example. This is the structure of film capacitor. Two foils and two dielectric films are wound into a cylindrical shape. The dielectric films are made of polymer. The thickness D of the dielectric films is approximately 1 micrometer. This is very thin compared to the width W, which is about 5 millimeters. This is another example, a multi-layer ceramic capacitor, MLCC for short. It consists of alternating layers of metallic plates and dielectric plates. The dielectric ceramic is made of barium titanate. MLCCs are among the most popular capacitors in the industry. Take the example of an MLCC, the thickness of dielectric plate D is approximately 1 micrometer. This is very thin, compared to the length L and width W, which are about 1 mm. Suppose that the positive charges are provided by a voltage source, and its voltage is V volts. Positive Q coulombs and negative Q coulombs are stored on the facing surfaces. The fringing effect is neglected. The charge density ρ on the surface is given by Q over A coulombs per square meter, where A equals L times W. With fringing neglected, according to section 5.3, E on the conductor surface is given by this equation. In a capacitor, E goes straight, thus this E is valid everywhere in the dielectric. The potential V at the surface of the upper conductor with respect to the surface of the lower conductor is derived as shown in this equation, where dl is the differential displacement directed as in the figure. E is substituted with the equation above. Rho is replaced with the topmost equation. This potential difference corresponds to the source voltage V. By definition, the capacitance of this two-plate capacitor C equals Q over V. Thus, C is given by this equation. Exercise 6.1.1. Pause the video and answer the problem. Find the capacitance. The answer to exercise 6.1.1. Pause the video and check the answer. Exercise 6.1.2. This is your homework. Pause the video, and answer the problem. Find the capacitance of MLCC. Exercise 6.1.3. This is your homework. Pause the video, and answer the problem. Show that the potential VR2 is given by this equation, and find the capacitance per unit length. The author of this material is Takeshi Furuhashi, Professor Emeritus, Nagoya University. If you have any questions, send emails to this address.